All right, and my first Stellafane was in 1979, so I'm an STM member. But today I want to talk to you about observing a different kind of star, one that you don't have to lose sleep over. The solar special interest group of the AAVSO is a little different from the other special interest groups. We look at one star and we look at it during the day. So the question that people sometimes ask is, why study the sun? I mean, it's right there. And that's the point. It's right there. It's the nearest star to the Earth. Obviously, that is not to scale. If it were to scale, we wouldn't be here to talk about it, right? But it's only 93 million miles away. So we can actually observe it in much greater detail than we can any other star in the sky. So by understanding the sun, we can apply what we have learned to understand other stars in our galaxy. There's a lot going on beneath the surface of the sun, literally. There's thermonuclear fusion of hydrogen to helium in the core, and the photons that are released are bouncing around, and then that causes a churning of the plasma closer to the surface. And then it doesn't stop there. We have the radiant sunlight that comes out and reaches us at Earth, and we have the outer layers of the sun as well. So we here at the AAVSO solar section are looking at just one small part of the sun, one small layer, but from understanding that, we can understand other regions of the sun. So what we do is we literally look at what we call the visible surface of the sun. Surface in scary air quotes because you can't stand on it. Not just because it's really hot, but because it's not solid. It is an opaque layer, meaning you can't see through it, of plasma, and it is always boiling. And this layer is called the photosphere, the light sphere. And that boiling is what's called granulation. How many of you in your childhood enjoyed old-fashioned oatmeal on the stove? Okay, some of you. Imagine taking that, throwing in some yellow food coloring, and then throwing in some raisins. And that's pretty much what you see on the surface of the sun. Now, many of us like to observe the outer atmospheres of the sun, the chromosphere and the corona. You can observe the chromosphere if you have a hydrogen alpha filter. You can see the corona if you have a coronagraph or if you go to total solar eclipses. These are wonderful, photogenic, interesting layers of the sun, but they are not what we observe. We strictly observe the photosphere, that visible surface. And what do we actually see? We generally see two different kinds of activity, which are called sunspots, or maculae, and faculae. Not faculty, faculae. Faculae are brighter appearing than average areas on the sun, and the maculae, the sunspots, are the opposite. They are darker appearing areas on the surface of the sun. And that word appearing is really important because sunspots are not black. They just appear darker than the area around them because they put out less light. And the faculae appear brighter because they put out a little bit more light. And they are actually easier to see along the edge of the sun, what we call the limb, because of something called limb darkening. At the edge of the sun, you are looking through more gas, through more plasma. You have more contrast, and that's what makes those faculae sort of pop. They look sort of like bright strings or bright patches on the edge. Now, why do the maculae and faculae appear brighter and darker? They're putting out more and less light because of temperature. And why do we observe these kinds of activity? Because frankly, they're the easiest to see. They're the most obvious kind of solar activity. We have been monitoring them since at least the early 1600s in a scientific way. So sunspots appear darker because they're about 1500 Kelvin cooler than the surrounding photosphere. The photosphere is about 6,000 Kelvin, about 10,000 Fahrenheit. The sunspots are about 4,500 Kelvin. If you could surgically remove a sunspot and hold it out with some incombustible tweezers, it would glow sort of a magenta color, sort of like the dying embers of a campfire. And the interesting thing about sunspots is that they're always changing. They are popping into existence, they get bigger, more complicated, and then they die away. They can individually last for hours, days, weeks, sometimes even into months. And we have records of these going back at least to the time of Galileo. Here we have some famous drawings from Galileo of sunspots on the sun. And the picture on the right shows the progression of sunspots from day to day appearing to move across the face of the sun. It is not the sunspots getting up and running across the sun. It is the sun actually rotating, carrying the sunspots with it. So this can be used to measure how quickly the sun spins. And the answer is it takes about a month. So what are sunspots physically? You will often hear them described as magnetic storms on the surface of the sun. They're places where the local magnetic field is somewhere between 10 to 40 times stronger than normal. How do we know that? We know that by something called the Zeeman effect, the way that a strong magnetic field actually impacts the light. It actually impacts the wavelengths that are emitted by that region of the sun. And we actually see a splitting of the spectral line. If you look on the far right, in the middle, hopefully you can see that there are 3 lines very close together. Not only are individual sunspots being born and dying, but the total number of sunspots is changing over time in a cyclical manner that is not a perfect pattern. Oh, we wish it were a perfect pattern. That would make life so much easier. It is roughly 11 years. Sometimes you'll hear it called 11.3. It can be as short as 7 years between maximum to maximum. It can be as long as 17. Well, actually, we don't know because we're only in solar cycle 25 that we've effectively measured. Those numbers could actually be more extreme. We just don't have data to show that. So the sun is actually considered a variable star. Because of those brighter and darker areas on the surface, the overall brightness of the sun changes. Thankfully, not by a lot, because that would really be problematic. On average, over the sunspot cycle, the brightness of the sun varies by about 0.1, sometimes 0.2%, which is not a lot, but it is measurable. The top graph shows you the changing overall brightness of the sun. And before you get all concerned by how far up and down it's going, please look at the numbers on the y-axis. It goes from about 1360 to 1362. It is not a big difference in brightness, but it is measurable. And the thing that's really confusing to people when they hear this about this the first time is that the sun is actually brighter at sunspot maximum. And I've proven that by having the graph at the bottom, which shows you the number of sunspots. The peaks in the number of sunspots matches up with the peak brightness of the sun. But there's a problem. Remember that sunspots are darker appearing areas that put out less light. So why should the sun be brighter if there are more darker appearing regions? Do you see how that makes no sense at face value? The key is that there are also these brighter areas that don't get as much press, the faculae. And the faculae more than overcompensate for the dimness of the sunspots. So here in these pictures, you can actually see how extended some of those bright areas actually are. And you can see how they can overcompensate. Not all stars have a lot of faculae. You may have heard of red dwarf stars that have large sunspots. And that can actually be a problem for people looking for transiting exoplanets, because is it an exoplanet or a dark spot on the surface of that star? Red dwarfs, they don't have these bright faculae. So when they have big sunspots, big star spots, they actually get dimmer, like a transiting exoplanet would make it. Another interesting thing about sunspots is that they're very sociable. They usually come in groups. They like to pair off. It's the buddy system. Remember on your elementary school field trip, you had to buddy up with somebody, right? The sunspots are kind of the same way. Now, as you'll see, you can have loner sunspots, but generally they tend to come in what we call bipolar groups. And so when we get to the idea of how do you identify a group of sunspots, looking for this buddy system can be very helpful. And the interesting, again, thing about a group of sunspots is that it changes over time. So from day to day, it will not only appear to have moved across the sun, but will also have changed in the number of spots and the appearance of spots. So what's going on? The full answer is it's complicated and we haven't quite figured it all out yet, which is one of the reasons why we study the sun. Here's the basic idea. The basic idea is that the magnetic field lines of the sun pop out at one of the pair of sunspots, loops around, and goes back in. If you will allow me a medical terminology, sort of like a hernia. Okay? Now, the magnetic field line coming out and going back in at the entrance and exit wounds, that restricts the motion of heat. And that is why the sunspots are cooler than the surrounding area. Now, when the magnetic field loops up and loops back down, magnetic field lines can actually cross. And that's not good. Imagine taking a rubber band and tangling it all up, and then it snaps, and you go, ow, because of the release of energy. The sun is basically going, ow, as the magnetic field lines tangle, cross, and what we call snap and recombine. And that energy is what makes the upper atmospheres of the sun, the chromosphere and the corona, much hotter than the surface of the sun. The corona, in some cases, 2 million degrees, right? So there's a lot of really cool physics going on there. And again, what I've explained is overly simplified and makes it sound like we understand completely what's going on, and we don't. But wait, there's more funky stuff going on that we can study. Again, remember that Galileo showed that we can see how fast the sun is rotating by watching the sunspots appear to move across the surface of the sun. But if you look at sunspots at different latitudes, you find that the sun doesn't rotate at the same speed everywhere. It actually rotates faster at the equator and slower at the poles. So I said it took about a month for the sun to rotate. It takes the equator around 25 days, and it takes very high latitudes around 34 days. Why can the sun do that? Because it's not solid. It's a ball of plasma. But because different parts of it are spinning at different speeds, the plasma gets all twisted around. And what do you think that's going to do to the magnetic field lines? Twist them around as well. So this is a model that's been around for a number of decades. As I said, it is a simplification. We are working on models that are more precise. This is called the Babcock-Leighton dynamo model. It basically says that the magnetic field of the sun starts out like a bar magnet, like the Earth. You have a magnetic north and a magnetic south. And the magnetic field lines are more or less going from magnetic north pole to south pole, what we call a dipole. But because of the differential rotation, you can see how the magnetic field lines start lapping each other, and they get all tangled. And this sets up a situation where the magnetic field lines make like little donuts, what we call toroidal. And this is what causes those bipolar sunspot groups. What happens is that over time, these toroidal field lines start to fragment, and it carries little bits of magnetic field to the north and south magnetic pole. Now, what have you learned about magnets and repelling and attracting? Do like poles attract, or do opposite poles attract? Opposites. So the south polarity fragments go towards the north magnetic pole. The north magnetic fragments go towards the south magnetic pole. They change the magnetic polarity of the sun. So we eventually restore a dipolar magnetic field of the opposite polarity. Now, this is where I have to say the sun did not flip over. It is not the rotational axis flipping over. It is the magnetic field changing polarity, okay? Again, I've oversimplified it, and I've said it very confidently like we know exactly what's going on. There are still a lot of details to be worked out here. But generally, this is what causes the sunspot cycle. If you want to have it as the simplest elevator pitch, because different parts of the sun rotate at different speeds, the magnetic field gets all tangled up, it snaps and resets about every 11 years. Sort of like kittens playing with a ball of yarn. If you've ever had kittens playing with a ball of yarn, it becomes a mess pretty quickly. Now, sometimes you can try to untangle it, but usually what you do is you cut it with scissors and you throw out the tangled part and you tie it back together. And hopefully it doesn't matter in the scarf you're making. That's basically what the sun does. It ejects, through solar activity, that tangled up magnetic field and starts fresh. And it's not solar flares that do this. Solar flares get all the press. It is these things called coronal mass ejections. Coronal mass ejections are huge bubbles of gas, of plasma, threaded with magnetic field lines that are ejected from the sun. And you can see how huge they are. And from that time lapse, you can see how quickly it happens. Tremendous amount of energy. When this magnetized plasma reaches the Earth, it can interact with our magnetic field. It depends on whether or not the polarity is opposite ours or in the same direction as ours. And we normally don't know the orientation until about 30 minutes out. So sometimes you'll hear, oh, there's a chance of an aurora, and then nothing happens. It's because all they know is that this bubble of material is coming towards us. They just can't measure the orientation because the satellites that measure the orientation are at one of the Lagrange points about 1 million kilometers out. But occasionally, if everything is aligned the right way, the energy is imparted to our atmosphere, and it can actually make the air glow. It actually gives us an aurora. But it can do a lot of things that aren't so pretty. Can actually increase the voltage in high tension lines and cause transformers to blow. Thankfully, with the engineering, it doesn't happen nearly as often as it used to, but you still have to, if you're the power company, be aware of these things because you don't want transformers being overloaded. It can pose a radiation danger to spacewalking astronauts. It fries the electronics of satellites, and it disrupts radio communications. And it also fluffs up the atmosphere, causing the atmosphere, the Earth's atmosphere, to rise, causing drag on very low satellites. The ISS has to make corrections every once in a while because we don't want its orbit to decay. Skylab, the first American space station, reorbited, nice word for burning up over the atmosphere, in the atmosphere, earlier than expected because the sun was much more active in the 1970s than we thought it was going to be. Anybody here ham radio person? Okay, so you've heard you got to watch out for sunspots. You kind of get an idea. It's those interactions that the sun's magnetic field has with the Earth's magnetic field and how that affects the propagation of radio waves bouncing off our atmosphere. So the American Radio Relay League keeps an eye on the state of solar activity. So hopefully you can see that if the sun's magnetic field were well behaved and we could accurately predict when maximum of sunspot activity would be, we could be forewarned and forearmed and know when to keep the astronauts from doing spacewalks, to make adjustments for the power company, and to go out and look at aurora. But it's not a perfect cycle. Remember, it is not every 11 years, and the height of each maximum is not the same. It varies by a tremendous amount. We are currently in cycle 25. In the top left graph, you see the red line and the blue line. Those are some predictions that they put out with high confidence before we started our cycle. In the bottom right, that red line was the prediction, which had actually been adjusted a few times. The black line is what the sun decided to do. Anybody see any connection between those lines? Because I don't. So the sun pretty much does whatever it wants. This is why we observe the sun. To help the models, to help the predictions. And we just need more solar cycles of data to put into computer models. So we are currently on the downward slide of cycle 25. You can see here, this is from spaceweather.com. You can see that the sun has been very active. The last 4 years, there have been no days with no spots. But days with no spots are useful data. So what do? How do we count? You don't just look at the sun and go 1, 2, 3, 4, 5. It's more complicated than that. What we first want to do is figure out how many areas on the visible sun are active, have at least one sunspot. So an active area is called a group, even if there's only one spot. That's called G. Then we count all the individual spots in all of the active regions, and that's S, the number of spots. And we use the system that Rudolf Wolf from Zurich Observatory in the 1800s started. We use the Wolf number because the number of active regions is more important than the number of individual spots. It is weighted by a factor of 10. So you take the number of active areas, the number of groups, you multiply it by 10, and then you add the overall number of spots you see. And then there is something called the K factor, which takes into account the peculiarities of the observer, their equipment, their visual acuity, their experience, et cetera, et cetera. It is not something you need to worry about. If you observe for the AAVSO, after you've submitted your 100th observation, we figure it out for you. What we do not accept, we don't accept hydrogen alpha observations. We are looking at the photosphere, not the chromosphere. We don't accept photographs or sketches. We need your observation, what you see on that day. We know that there are satellites that have pictures every day. You can't just call up the picture from the internet and count what you see on the picture. That is not what we're talking about here. And if you observe with your friend, each of you needs to put in your own observation. Because each of you, even if you are using the same telescope, will see different things. And so why are we so persnickety? The value of our data is that we've been doing this at the AAVSO since World War II. And other observatories have been doing it longer than we have. And we need to aggregate all of the data we have, which is only 400 years taken in total. So we have to be able to compare one set of data to another. So we all need to use the same technique so that we can compare apples to apples. Right? Hydrogen alpha is wonderful, valuable, great. It is not what we collect. It is not part of our scientific mission. And to give you an idea, a number of years ago, some solar scientists took AAVSO data and data from other observatories and used it to recalibrate historical records of sunspots to try to get a better feel for what the sun was actually doing several hundred years ago. That's the value of what we do. And that's why we're very persnickety about making sure that we all observe the same way. So if you'd like to get involved, and we hope you do, go to the AAVSO website, go to the Solar Interest Group, and you will get a whole pile of resources that will allow you to get started. For example, we have our Solar Observing Guide, which is published in a number of different languages, because we are an international organization, regardless of the name American in the title. And I'm going to spend a bit of time talking about how to do this safely, because I've told you why we do it, and I've told you sort of how we count it, but how do we keep ourselves safe? I've been observing the sun since 1989. Any problems to my vision are not due to the sun. Trust me. They're due to being 62 years old, okay? We have about 70 observers around the world who regularly observe the sun. About half of them use what we call projection, and the other half use a filter. If you want to know, I personally use a filter. Projection is good in a sense because it is not only safe for your eyes, but it's also safe. It's safe for your eyes, but not for your telescope. So if you want to make sure that your eyes have absolutely no chance of anything ever happening to them, projection would be the way to go, but you're putting your telescope at risk because you are not filtering the light that is coming in. Please do not use this method with a catadioptric, right? The heat will build up inside the telescope and it is not pretty. You also want to make sure that your image is in the shade so you can actually see it. So you notice that there is sort of a collar around it. And this is also a good time to point out that we're not using big telescopes. We're using small telescopes, a couple of inches in aperture. If you have a larger telescope, we welcome your observations, but be aware that you may have to stop it down. Okay? Please, again, do not use your naglers to do this, if you have them. And please remove or cover your finder scope. And please, in the name of all that's holy, keep all body parts and small children out of the light path. Okay? You don't want to we used to do this in a lab up at UConn. And one kid's like, why is my arm hot? Well, because his arm was in the light path. Don't do that. A filter protects both your eyes and the instrument. A filter prevents 99.99 something percent of the infrared, visible, and ultraviolet light from entering the telescope. Your filter has to go on the aperture end. Back in the 70s, there were some cheap Japanese refractors that came with solar filters that you screwed onto the eyepiece. That ended up about as badly as you can imagine, right? So you want to prevent the light from entering in the first place. Again, remove or cover the finder scope. Make sure the filter fits snugly over the aperture, and check your filter every single time for any imperfections. Basically what you do is you look at it, do a visual inspection, then hold your filter up and look at the sun through it and make sure you don't see any bright streaks, cracks, dots. So people say, but if I can't use my finder scope, how am I going to find the sun? You minimize the shadow. If your telescope has a nice round aperture, you just minimize the shadow so it looks like a nice round circle. And the sun should be close enough to in the eyepiece. Now here's an interesting fun fact. If you have eclipse glasses, you can actually see large sunspot groups. If there's a group of sunspots that is roughly on the same order as the size of Saturn or Jupiter, you can see them with your eclipse glasses. And we actually have naked eye sunspot records going back historically hundreds, if not thousands of years. So here's my disclaimer. You are responsible for safely observing the sun. Not me, not the AAVSO, it is you. You must check your equipment every single time you observe the sun. Please don't rush, please don't make shortcuts. So once you've made your observation, we want you to submit them to us. We are currently using a software called WebOps, which you can get from our AAVSO website. And you basically get an observer code. If you've had to have an observer code for observing stars at night through the AAVSO, same observer code, same password. And it actually allows you, it has pull-down menus where you go in and you just pop in your data. The number of groups, the number of spots, it calculates the Wolf number for you. You put in the day, the time, the hour, the minute, any remarks that you have. We are currently working on updating the software. Brian, any idea when that might be making any changes? What was that? Later this year. Okay? But I don't expect it'll be horribly different. It'll just be a little tweaky, yeah. And so what do we do with your data? It not only goes into our database, but every month we put out the solar bulletin, which you can get for free from the AAVSO website, from the solar page. And the number of your observations is listed by your name and observer code. So you can feel good that not only have you contributed to science, but you actually have your name there as someone who has actually done this. So people will sometimes ask, how do I improve as an observer? When the sun is really visibly active, how can you tell one group from another? And the answer is, like anything else in life, it's practice and experience. So after the bulletin comes out, compare your numbers with what's in the bulletin and see how close you came to the average. Here's one of my early observations. It's a hot mess, complete hot mess. But that's how I learned, by comparing, by doing the observation and comparing to what came out with the solar bulletin every month. And that's how I got better. So they tell you to come to the dark side because they have cookies. They lied. Dark side does not have cookies. I don't know that we have cookies either, but we have the sun. We have that bright star out there, and we would love for you to be one of the members of the solar interest group of the AAVSO and to safely observe the sun and to add to our understanding of our star and to help us someday be able to make predictions of the solar cycle. So there is the email address. It's just solar@aavso.org. And I thank you very much for your attention, and we'll be happy to answer any questions that you may have. Frank, is that you? Frank is one of our longtime observers. He is awesome, and he is another person that you can talk to about getting started in solar observing. Yeah. Yes. How long does it take me to do everything, including setting it up? About 15 minutes. But that's because my telescope is set up. I don't break it down. I have a dedicated telescope that I use for observing, and I just bring it out, and I just do the safety check, put the filter on, and then do my observing. You observe once a day. Please only observe once a day. And it only takes me a few minutes to really just... I personally sketch, and then I make a note of also the numbers. So what I personally do in that picture, that really god-awful picture, I make my own little numbering system for how many, like where all the groups are, and then I make a column where I say how many there are. So I have my G and I have my S, the number of groups and the number of spots. And one thing that's interesting is, you see that number 2, the thing it's by itself, number 2? That counts as both a group and an individual spot. So if the sun had one spot on it on a certain day, the Wolf number would be 11, one louder, because it would count both as a group, and you multiply that by 10, plus as an individual spot. So it would be 10 plus 1 is 11. So the sunspot, the Wolf number goes from 0 to 11. There's nothing in between it. Yeah?
Is there a preference or frequency of observations? Like you said, you observe every day. Is there like a requirement, or is it just whenever you can get to it? Is it helpful?
Whenever you can get to it. We would love it if you had so many sunny days that you could observe every single day of every single month. But we know that you can't do that. So whatever you can do, we appreciate, because there may be a day when there are relatively few people who are able to observe, but you're one of the ones who can. So don't think, oh, I only submitted 3 observations this month. That's 3 more than 0. So do whatever you can. Yes?
Is there a preferred time of day to do the observations?
You will hear different things said by different people. Obviously, when it is higher in the sky, you're looking through less atmosphere, right? So that's always a good thing. You want to, like when you're observing stars at night, you don't want to look at them near the horizon. You want to look at them when they're higher in the sky. But usually that's when there's more heating, and so the atmosphere might be more turbulent. So I tend to observe personally around 10 in the morning. That seems to work well for my setup. It's high enough in the sky. It's above all the stuff. You also want to try to observe, if given a choice, don't put your telescope on or looking over a blacktop asphalt parking lot, because air currents. So looking over grass is better. So these are, again, some of it depends upon your observing, the difference is about your particular observing. But whenever you can, please do. Yes?
Chris, do you shift to a higher power eyepiece to understand the structure of the groups?
You can do that. What I tend to do personally I'm using a larger telescope than a lot of people. I'm using a 6-inch, and I tend to look at a full disc. And I have used the same eyepiece for years. And so I look and see what I have. And the point is consistency. Because since I'm using the same telescope, I try to observe at the same time every day. I observe from the same site every day, using the same eyepiece. When they calculate my K factor to get me sort of weighted in with the masses, it's reliable because whatever I'm messing up or whatever deficiency I have, it's already being taken into account. If you start, if that's something you're going to do every single time, consistently, then that's great. Because when you start observing, we ask you that information about your rig and about where you're observing from. So the point here is to do the same thing all the time. It's that consistency that's really important. Yes?
What filters will show the sunspots instead of just looking like a red blob? And where can I get that?
You want a telescope that can actually see sunspots, basically? Oh, filter. You can use, there are Mylar filters, there are what we call metal on plastic, there are plastic ones. I use metal on glass, I use 1,000 Oaks. Basically, it's metal evaporated on glass. There are filters. Frank, what do you use?
Mylar filter. Basically, any white light filter will do the job.
Yeah.
Get a sheet of Bader film and make your own.
Yep, you can make your own with Bader film. So the key is to obviously go to a reputable dealer, do your homework. If you want to contact us and ask for some suggestions, everybody observes slightly differently with different materials, and we can give you some options. But it's not like a hydrogen alpha, which can be really expensive.
So when I went through a Mylar filter, it just looks like a red blob.
When you're just looking at red, black, what do you use? What is your setup again?
When I use a Mylar filter,
For your Mylar filter, just looks like a blob, really? What's your aperture? Huh. That is quite peculiar. We'll have to talk. Because you should definitely be seeing, given what the sun's been doing the last couple of years, you should be seeing stuff. Yeah, that's very peculiar. Did you have a question?
I was going to ask, what's the minimum aperture you'd recommend to see enough detail in the sunspots?
I think we have people down to 60 millimeters who actually contribute. But again, it's consistency. If you're missing sunspots because they're too small for you to see, you're consistently doing that, and that will be built into your K factor. Yeah?
At the sunspot lows, do you have days where you just get zero sunspots?
Oh, yeah. I mean, we haven't had any in the last few years, thankfully. But yeah, you go out there, and as one of my students declared, it looks like Winnie the Pooh's butt because the sun looks orange through the filter I have. So it's this big orange blank circle. Yeah, but that's useful information. That tells us something about what the sun's magnetic field is doing today, right now. So I can't say that it's fascinating when you get day after day of no spots, but it's important data. And it's more than made up for on the days where you look at it and go, man, you need some penicillin. That's just not good. Spots everywhere. Any other questions? Yes?
what is the accuracy at which periodically you identify the number of coronal mass ejections? The only reason I'm asking this is because the sun rotates and it takes 24 to 27 days sometimes. So when there are sunspots at the backside of the dark side, I'd say, of the sun, and then there are coronal mass ejections right when it rotates because they disappear or they flare up.
Yeah, no, the sun is a three-dimensional object, which you sometimes lose when you see these flat pictures. So when there's a coronal mass ejection, the material is spewing out in some direction, but it's coming out like, a spray spread out a bit. And so the question is, where is it actually aiming? And where is it actually, will it actually hit the Earth, interact with the Earth's magnetic field? So yes, there can be times where they go, there's one coming, but it could miss us. And then there are the ones that are on the back that are clearly going in the opposite direction, that are not going to impact us at all, that are just seen by the sun orbiting satellites. So yes, they can be wrong. So please be kind when you hear somebody say, oh, there's a chance of an aurora tonight, and nothing happens. They're predicting as best as they can. Anything else? All right, well, thank you very much for your attention.